Good morning, everyone. My name is Mike Laverick, and today I'm going to talk to you about how our research team is integrating the Opensky Network data into our GNSS-R climate monitoring research. Our team is composed of the University of Auckland, the Ohio State University, University of Michigan, and also our collaborators at Air New Zealand. Now, my background is in astronomy and astrophysics, so I'm neither an expert in climate science nor in aviation, so hopefully everyone should be able to follow along with the presentation I'm about to give. So, what is GNSS-R? Well, simply put, it stands for Global Navigation Satellite System Reflectometry. I've practiced that one a lot. So, most of you are probably aware of what GNSS is. It includes navigation systems such as GPS, Galileo, and it emits in the radio band. It's responsible for keeping pretty much every single vehicle on the Earth aware of their current position. So in a similar way to radar, those GNSS radio waves can reflect off the surface of the Earth, and if you can measure the change in signal strength before and after this reflection, you can infer some of the properties about the Earth's surface. Now, as we all know, the majority of the Earth's surface is water, so we'll start there. Good explanation for GNSS reflections is if you consider the case where moonlight is reflecting off the surface of a lake. If the wind is calm, then so is the water, and we get a nice reflection of the moon with all of the moonlight reflecting and hitting us. If the wind is a bit wild, the water becomes a lot more distorted and ripply, the image of the moon is scattered, and it becomes much less bright. So this is also the same case as for GNSS reflections. If the reflected signal strength is high, or bright, we know the water on the Earth is calm, and thus the wind speeds above that water are low. If the signal is low or faint, then the water is rough and the wind speeds must be high. So this is the principle behind the NASA Cygnus mission, which is a series of 8 microsatellites with GNSS-R detectors on board. These are designed to measure the wind speeds and the structure of tropical cyclones. Each one of these 8 microsatellites can receive 4 GNSS signals simultaneously. And if we look at this diagram on the page, we can see an example of a Cygnus receiver orbiting around the Earth, and we can see how the receiver detects reflected signals from 4 GNSS transmitters simultaneously. The receiver can also receive GNSS signals directly from the transmitters themselves, and thus we can compare the direct and the reflected signal strengths against each other to determine the change in signal due to the reflections, which allows us to derive these surface properties. So, we have 8 microsatellites. Each one of these are receiving 4 reflections from the Earth's surface, resulting in 32 reflection tracks as the Cygnus orbits around the equator every 90 minutes. Over time, these tracks build up, which allow us to map out the structure of hurricanes and cyclone as time progresses, as these images show. You can see down here the yellow part is the center of the cyclone as it moves towards the US, and it's a pretty cool way to monitor potentially dangerous weather fronts and plan for their arrival. But it turns out that the Cygnus data can be used for much more than just hurricane structures. In actual fact, what you can do is you can use the data to quantify surface reflectivity and soil moisture content. You can map out waterways despite thick vegetation, and you can actually measure and monitor the ongoing impact of hurricanes, tsunamis, and other causes of flooding. So I've linked the paper down at the bottom here to the Nature paper, which describes some of the achievements that the Cygnus mission has managed to achieve. But to go over them briefly here, the first one, soil moisture. So, this lovely figure of Australia here. On the left 2 panels, we have a dedicated soil moisture monitoring mission. In red, we have a change in soil moisture going down, and in blue, we show an increase in soil moisture. Now, on the right-hand side, we see the Cygnus data for Australia over the same time period. The Cygnus data shows the change in signal strength over time, blue being an increase and red being a decrease in signal strength. And we can see that these 2 plots, despite measuring soil moisture content and the other measuring just reflection signal, they're pretty in sync, which tells us that actually Cygnus can measure and quantify soil moisture content from space, which is pretty impressive. Moving on, we can see a detailed figure here showing the Amazon rivers. The Cygnus data has been used to actually map out the Amazon rivers to a fairly high degree of accuracy. Blue showing the strongest signal strength reflections, yellow showing the lowest parts, and what you can quite clearly see the vein-like structure of the rivers. Now this is despite all of the thick vegetation of the Amazon. There's lots of trees in the way, but fortunately radio can pierce through thick vegetation and even weather clouds quite easily. Now, of course, moving on to the next one, GNSS-R can be used for not just monitoring and predicting the hurricanes themselves, but we can actually monitor the ongoing impact that they have when they arrive. So here we see a 4-day period of Hurricane Harvey as it hit the US coast. We can actually see that as the storm hits, flooding starts to occur, and so too does the Cygnus signal, which we can see starts showing an increase in strength as the days progress. Now what this actually does is it lets Cygnus start measuring the ongoing flooding, and we can monitor it from space rather than trying to do risky aerial surveillance through the ongoing hurricane. So, the Cygnus mission was so successful that NASA's actually now developing the next generation of GNSS-R receivers. The next gen receiver can receive 20 simultaneous signals instead of 4, has a much better spatial resolution and temporal sampling, and it has a more accurate sea surface height detection, which will allow for early tsunami warnings. But wait, isn't all of this about satellite stuff? Well, don't worry, Air New Zealand has come to the rescue. Now we're moving on to the flight context. So NASA and Air New Zealand have actually partnered up to work on this project, and Air New Zealand is going to certify, install, and fly the next generation of GNSS-R receiver. So it's going to work in pretty much the same way, except instead of an orbiting Cygnus satellite, we're going to have a plane that flies around the planet. However, because the plane is going to be much closer to the ground, it's going to receive a much stronger reflection signal, and thus also have a much more precise geospatial accuracy. So, a bit more detail. The craft that we're going to mount it on is a domestic commercial aircraft. It's going to be a Q300 in the Air New Zealand fleet. The receiver is being built in collaboration with the Civil Aviation Authority, and so of course it's got to ensure that it has no impact on flight operations. We only transmit data back to the ground station when we're on the ground, and the box has pretty much got to exist autonomously. Mounting a science payload on a commercial craft is a pretty novel concept. We're actually hoping that this trial or demonstration can enable more scientific research opportunities in the future. There's a lot of commercial crafts around the world, and if they can all start doing some climate monitoring, we're going to get a lot of data in. So why New Zealand? So here we see a coverage comparison between 3 years of Cygnus coverage data and 1 year of simulated Q300 receiver data. As we can see, yellow on the left-hand plot shows a huge amount of coverage, and blue shows pretty much no coverage. And the reason for this is because the Cygnus satellites are limited in latitude coverage. They orbit around the equator, so there's only so far down that they can get. They were made to monitor tropical cyclones. But we still do have a slight overlap with New Zealand. And so by mounting the receiver on an Air New Zealand Q300, we can both extend the coverage to include the majority of New Zealand, but we can also cross-validate the new detector against the Cygnus satellite detectors, and if we put in further more ground monitoring as well in New Zealand, we can do 3 different data sets that we can use to cross-validate each other and calibrate each other. So New Zealand has a pretty impressive and dynamic coastline. Being able to monitor these remotely and frequently via aircraft is a pretty big boon for research and coastal conservation and protection. Similarly, monitoring inland forests, grasslands, wetlands, and agricultural areas is likewise just as invaluable towards conservation efforts. So, the project has been under development for the past few years. Design of the aircraft integratable detector is well underway between NASA, Air New Zealand, the University of Michigan, and of course the Civil Aviation Authority. Fabrication of the device has already started, and then COVID hit. So now, of course, as the rest of the world have also experienced, COVID's delayed the project somewhat, with the impact on airlines, which has been substantial. Fabrication's been delayed a little bit. Shipping between the US and New Zealand has been difficult. There's a few delays, but we're still on course to lift off in 2021. But for now, it means we've got a bit more time to focus on the data workflows and pipelines in preparation for liftoff so that we can hit the ground running and then take off. So finally, we're coming around to the real point of why we're all here, OpenSky. We're going to need some real data to simulate with. But we don't have real data yet, so in place of that, we're going to use some cutting-edge simulations to generate synthetic GNSS-R data. Naturally, to do this, we need flight data. If you want to simulate an aircraft-mounted GNSS-R receiver, you need some flight data. So, initially, the simulation codes were built using flight-aware data, which I'm pretty sure most of you have heard of before. However, of course, FlightAware is a commercial company, and so getting hold of this data is pretty costly, and it's very limited in terms of what we can do with the licensing, i.e., it's very difficult for us as academics to share it with each other without each having to separately buy the same data. If we want to simulate lots of flights and share lots of data with the world, it's going to cost a lot of money. But fortunately, OpenSky comes to the rescue. So, what data do we need from OpenSky and what data would we like? Well, at minimum, we'd like 1 month of state vectors so that we can simulate a single Q300 craft and get an idea of the coverage we'd expect to see from a detector mounted on one. Ideally, we'd like 1 year of state vectors for all Q300 crafts in New Zealand. It's about 20 flights, 20 crafts. And we'd also like to have some live tracking of at least one Q300, if not more, in the cherry future where we manage to get more than one detector mounted. Fortunately, the Opensky Network historical database and the API can provide everything that we want and everything that we need. So, after a little back and forth, we managed to get access to the OpenSky historical database. So I just want to say a big thank you to the OpenSky team for access. Thank you very much. After a little bit of work, we managed to query the historical database for all Q300 state vectors for the whole of 2019. A little scripting, and we can pull all that data automatically. And this resulted in over 20 gigabytes of raw flight data that we needed to then process and input into our simulations. Now, of course, anyone who's dealt with data before knows, or with raw data before, you need a bit of pre-processing before you can use it, especially so before it goes into the science simulations. So first we need to separate all of the data into the individual crafts. This is fairly easy. We do it by ICAL24 number. We then needed to split the year of craft data into individual flights. This was a little tricky. We had to come up with a little definition of what a flight was, but not so difficult. We then needed to derive a start and an end destination airport from the raw data. Now this was a bit tricky. The coverage in New Zealand is a little patchy, but we managed to come up with a little algorithm to determine which airport the flight came from and which one it's heading to based upon its current positions and its heading. Once we know its start and end airports, we can then extrapolate the data and interpolate to backfill all of these missing gaps. And this allows us to produce a full flight, airport to airport, with full latitude, longitude, all coordinates and speeds, all the way down to a 1 second interval, ready to plug into our simulations. We did this for all 50,000 flights of 2019, which is a little bit of processing. And now I'll show you an example of one of the ones that we did. So here we can see a flight from Auckland to Kerikeri. Now in blue we see the raw OpenSky data, in red we see the synthetic data that we had to interpolate and extrapolate. Now what you might notice is that the end airport Kerikeri is actually red when we get there. It's outside the coverage of OpenSky, and so it's a little tricky to determine an airport when it's outside of the coverage. But like I said, using heading and locations and a little bit of luck, we managed to figure out the airports that they came from and headed to. And once we've got that, we can fill in all of the data for the simulation. So now that we've got complete flights, for 50,000 flights, we can plug in all of those state vectors into our simulations, and we can now simulate the predicted locations and strength of all of these GNSS reflections from these 20 simultaneous satellites orbiting. Doing this, we can predict the geospatial coverage, and we can start building up an idea of what we'll actually see from these aircraft as they fly over. Now, of course, there's lots of other data that go into these simulations. They're pretty cutting edge. You need to know the satellite locations at any given time. You need coastal and terrain maps, which are gigabytes each. You need antennae field patterns to try and determine signal strength. There's a lot of work that goes into it, but I'm not going to bore you with those details. Instead, I'm going to show you a nice video of all of the data that we've synthesized afterwards. So, I'll show you a sped up flight here. It was about a 30-minute flight. It's now compressed down to 1 minute. And this is completed with all of the GNSS-R reflections. So in gray, we see the flight, and in yellow, we see the flight path. And these pink worms are actually the reflection points from 20 simultaneous GNSS satellites. So as the flight progresses, we can see that these worms start following the flight path, with new worms sporadically appearing over the ocean and heading towards the aircraft, some of them diverging away, and all of this is a result of the satellites, or the geometry of the satellites orbiting around Earth relative to the flight. It's pretty cool to visualize how these reflections follow the flight, and it shows the kind of geospatial coverage that we'd expect. So as the flight lands, we can see all of these reflection points pull in closer to the flight, until they all eventually converge as the flight lands. So, the computations can be a little demanding in terms of computer resources, but our ideal goal is to be able to plug in the live API from OpenSky into the simulations. Currently, we can use the API to track our payload, letting us know when to expect to receive data from the on-ground flight, and generally let us track our receiver. But it would be great if we could also able to forecast the data coverage and thus allow us to prioritize the data processing of particular flights. So for instance, if we see a flight had passed near an area of flooding or coastal activity, we can then prioritize that as the data gets shipped off the flight. So to wrap up, I'll briefly show that we also investigated the OpenSky coverage in New Zealand for 2019 and also looked at it in August 2020. We noticed that the coverage in the middle in the North Island actually dropped out for a good chunk of 2019, and that the Northlands, the area that overlaps with Cygnus, was just out of our sensor range. So as a result, at the Auckland University, we're planning to install a couple of additional ADS-B sensors to fill in the coverage gaps around New Zealand. So if we look, these are the three locations, the northmost one, to fill in the coverage that's complementary to Cygnus. Over to the right, this is to fill in Gisborne, which is blocked off by a mountain range. A lot of the flights do go there. It's pretty easy to predict that they go there, but we'd like to have full coverage. And also to put an additional sensor in the middle of the North Island, just to bulk up the coverage a little bit more. So, all that remains now is to thank you all for listening. Thank the OpenSky team for organizing this conference and producing such a cool data network. Thanks to my colleagues who've put in the hard work that they've done to realize this pretty cool project, and to open the floor to any questions that you may have. Thank you.